the integral test and p-series. First, we discussed the integral test, and here it is possible to determine whether or not a series converges or diverges by equating the series with a comparable integral. You recall from Calculus 1, Chapter 4, that the integral is defined as a series, the summation of rectangular slices that are said to sum up the so-called area under a curve. Well, if that be the case, then the summation and the integral are relative. So if whatever happens to one, then the same happens to the other. So if the integral converges, then the series converges. If the integral diverges, then the series diverges. And so here we consider that. First, let f be positive, continuous, and decreasing. So that's the stipulation that we put on the function for x greater than or equal to 1. And we say that the sequence a sub n is the same as the function, where the domain would be the set of natural numbers. The domain would be the values of n. Right? So if that be the case, then convert the series to an integral, and then from there integrate. If the infinite integral gives us convergence, then the series converges. And then if the integral gives us divergence, then the integral diverges. So first, confirm that the integral test can be applied, and that is, are the values for f, or the sequence values, are they positive, are they continuous, n, are they decreasing? For number 9, yes, that is the case. Then use the integral test to determine the convergence or divergence of the series. Well, first, it's probably good to be able to determine what this is. I need to work on my summations. So his summation is n goes from 1 to infinity. This looks like the natural log of n plus 1 divided by n plus 1. So here we say this is comparable to the integral from 1 to infinity of the natural log of, here we're going to use x, too much, x plus 1 divided by x plus 1 dx. Okay. Now, let's consider this, that if you let u equal to the natural log of x, then du picks up that x plus 1 dx downstairs. So here du is 1 over x plus 1 dx. So if this be the case, then we have the integral from 1 to infinity of, this looks like u du. So we integrate this, so we have u squared to the second. Here we evaluate the integral from 0 to infinity, from 1 to infinity, excuse me. But u was the natural log of x plus 1. This is to the second power, all over 2. Evaluate that from 1 to infinity. Well, this gives you the natural log of infinity squared, right? All to be squared divided by 2, which is infinity. So the integral diverges, So since the integral diverges, then the series diverges. This implies the series diverges also. What about this one? It looks like we can use a u du. This is comparable. It's not equal to, but it's comparable to the integral from 1 to infinity of 1 over 2x plus 3 to the third power dx. Is the function positive? Yes, it's positive. The values are decreasing. 1 is fixed. These terms here gets larger, right? And it's continuous on the interval from 1 to infinity. Right? It's not continuous here for -3/2, but n is going from 1 to positive infinity. So the integral test can be applied. Let u equal to 2x plus 3. So du is 2 dx, and 1/2 du is dx. So we get 1/2 times the integral from 1 to infinity of the u to the -3rd power du. And so here we get 1/2 times u to the -3 plus 1, so we get -2. Divided by -2. Terms evaluated from 1 to infinity. So this is -1/4 times 1 over u squared, but u is this 2x plus 3 squared evaluated from 1 to infinity. So this equals to, and if I can use the notation here, but this is -1/4 times 1 over infinity to be squared as terms go to infinity. Well, that limit there gives you 0, and then so this is plus the 1/4 times 1 over, plug in x equal to 1, we get 2 plus 3 to be squared. Well, this just gives us 1 over, this is 2 plus 3 is 5 to be squared is 25 times 4, we get 1 over 100. We get a number, that's the key. You know, that first term here goes to 0, we get -1/4 over 1 over 2b plus 3 to be squared. Here as b goes to infinity. So that term gives us 0, and then plus this term here, 1/4 times 1 over the 2 plus 3 as when x is equal to 1 to be squared. So we get a number, fixed number. So the integral converges. So since the integral converges, the series also converges. Let's look at this one. This is comparable to the integral from 1 to infinity of 4x over 2x squared plus 1 dx. Again, a u du substitution. Let u equal to 2x squared plus 1. So du is 4x dx. That's the numerator exactly. This is the integral from 1 to infinity. Notice here that we have 1 over u times du. And so this gives us the natural log of the absolute value of u evaluated from 1 to infinity. Well, let's see. This is the natural log of the absolute value of 2x squared plus 1. Right? And this is evaluated from 1 to infinity. This is the natural log of infinity. This goes to infinity. So the integral diverges. Thus we conclude the series diverges. I'm watching you.